You know, the James Webb Space Telescope has been blowing our minds with these incredible new views of the universe. But what if I told you that scientists are already working on what comes next? And it's not just a small upgrade. We're talking about a telescope that's 7 times larger, with a mirror made not of glass, but of liquid.
So to really get why we need such a wild new idea, we've got to talk about the limits of what we can see right now. We're getting these jaw-dropping images of galaxies far, far away. But when it comes to planets outside our own solar system, exoplanets, well, we're still kind of fumbling around in the dark.
And that really is the big question, isn't it? We know they're out there. I mean, thousands of them, orbiting all these distant stars. But knowing a planet exists and actually seeing it, yeah, those are two completely different ballgames. The challenge is just immense.
Take a look at this. This right here, this is the absolute best we can do. And no, that's not a blurry photo or a mistake. That single little dot is our best picture of Proxima Centauri b, the closest exoplanet to us. This is the very limit of our most powerful telescopes.
So what does a single pixel not tell us? Basically everything. We have no clue if it has oceans or continents. We can't see clouds or weather. We have no idea what's in its atmosphere, and forget about seeing any potential signs of life. To answer those huge questions, we need a much, much bigger eye on the sky.
And that brings us to the solution. It's a project called FLUTE, the Fluidic Telescope. And the core idea is just as brilliant as it is, well, audacious. The plan is to solve the size problem by just getting rid of a solid mirror entirely.
Just to give you a sense of scale here, the main mirror for this new telescope is planned to be about 50 meters across. That's almost the length of a football field. It is an absolutely massive leap in size and in power.
Okay, let's put this side by side. James Webb's mirror, which is an engineering marvel, is about 6.5 meters across. Flute, around 50 meters, so 7 times wider. But here's the key. Because of how area works, its light-gathering power will be a staggering 77 times larger. And it does it all with one single, giant liquid mirror.
So I know what you're thinking. A liquid mirror the size of a football field in space? How in the world is that even possible? It totally sounds like science fiction, but it's actually built on a really simple and, honestly, beautiful principle of physics.
And get this, the idea isn't even new. The concept of using a spinning liquid to create a parabola, which is the perfect shape for a telescope mirror, has been around for centuries. Isaac Newton himself was the first person to figure out its potential for looking at the stars.
And the way it works is just so cool. You just pour a reflective liquid into a round container and you spin it. As it spins faster and faster, centrifugal force pushes the liquid out and up the sides, and the laws of physics just take over, forcing the surface into a mathematically perfect parabola. No grinding, no polishing, just pure rotation, creating a flawless mirror.
And look, this isn't just some theory on a whiteboard. It has actually been done. The Large Zenith telescope up in Canada used a 6-meter-wide liquid mirror made of mercury, and it worked for over a decade. So the concept, it's totally proven.
Okay, so if the tech works just fine here on Earth, why go through all the incredible trouble and, let's be honest, expense of putting one in space? Well, the answer, like it so often is in astronomy, is gravity.
It's a totally fair question, right? That telescope in Canada worked, but there's a catch. On Earth, these liquid mirrors have a fundamental problem that stops them from getting really big and lasting for a long time.
Here's the deal. On Earth, gravity is always pulling down on that liquid. It's constantly fighting against that perfect parabolic shape, creating tiny little distortions that just get worse and worse over time. But in the microgravity of space, that whole problem just vanishes.
Okay, so space is the perfect place for a giant liquid mirror. Awesome. But that brings us to the next huge challenge. What liquid do you actually use? And the answer is definitely not as simple as you might think.
I mean, the obvious first choice is mercury, right? Just like the telescope in Canada. But for a space mission, mercury is a total non-starter. For one, it's incredibly heavy, which makes launching it into orbit crazy expensive. Plus, it's really sensitive to the wild temperature swings it would face out in space.
So scientists had to go back to the drawing board. They tested all sorts of things. Gallium was reflective, but its melting point was all wrong. Plain old salt water actually behaved really well in zero gravity, but, well, it wasn't reflective enough to be a mirror. But this is where the real genius kicks in.
The solution was to take that super stable salt water and give it an upgrade.
Scientists figured out how to infuse it with these tiny, tiny nanoparticles of silver and aluminum. This didn't mess with its great behavior in zero-G, but it turned the liquid into a super reflective surface, a perfect space-age mirror.
So, with the physics proven and this new space liquid invented, let's bring it all back home. Back to the whole reason for all this incredible work. Finally seeing exoplanets in amazing new detail.
And you know, this isn't some far-off pipe dream. The groundwork for this has been laid for decades. The concept was proven on Earth back in 2003, and just recently in 2022, the special liquid was tested successfully up on the International Space Station. Right now, NASA and the Israeli Space Agency are designing the mission, aiming for a launch sometime before 2040.
So what does 77 times more light-gathering power actually get us? Here's the payoff. We will be able to see distant exoplanets with the same level of detail that we see Pluto with today. I mean, just think about those incredible, clear images of Pluto's mountains and ice plains. Now imagine seeing that on a planet orbiting a different star.
This is a complete and total game changer. For the very first time, we'll be able to actually map the surfaces of these alien worlds. We can analyze their atmospheres directly, looking for things like water or oxygen or methane. We'll go from seeing just dots of light to truly exploring new worlds. And that leaves us with this one final kind of profound thought. For all of human history, the planets in our own solar system were the only worlds we could ever dream of seeing up close. Soon, that's not going to be true anymore. So when we finally open this new window to the universe, the question really isn't if we'll find something amazing, it's what will it be?